Hello guys, welcome on Tesla Adventures. In this video today we'll going to discuss the level 1 problems based on gravitation and satellite motion. So you can see that in this first problem there is a satellite or a spaceship which is revolving around the earth in a orbit which is very close to earth's surface, which means that its orbital velocity will be under root of gm by r, and we know that the value of gm is equal to gr square. So VO is equal to under root of gr. This is the orbital velocity, and this value is equal to 7.92 kilometer per second. And now we know that the escape velocity from the orbit is root 2 times of the orbital velocity. Therefore, the escape velocity will be root 2 into 7.92, which is equal to 11.2 kilometer per second. And therefore, we need to find out the additional velocity with which we should impart to this satellite to make it escape is equal to this is 11.2 kilometer per second. So additional velocity is 11.2 minus 7.92. So this would be 3.28, approximately 3.28 kilometers per second. So this additional velocity we should impart to the satellite so that it escapes from the gravitational pull of Earth. Now we move on the next question. In this question, you can see that there are two stars. The mass of one star is m and the mass of other one is 16m. The radius of smaller star is a and the radius of bigger star is 2a, and the distance between the centers of these two stars is 10a. And there is a body of mass m which is fired straight from the surface of the larger star towards the smaller star, like that. So first of all, we need to find out the distance between the center of the smaller star and the point where gravitational field intensity vanishes, which means that is the neutral point. Neutral point is the point where the gravitational field of both of these two stars will cancel out each other. So we have to find out the distance of that point from the smaller star, and also in the B part we have to find out the minimum velocity with which we should project this mass so that it just reaches the surface of the second star, smaller star. So let us first of all calculate the first part. So we know that the point where the gravitational field intensity will vanish is, let's suppose, at a distance of x from the smaller one, and this distance would be 10a minus x. Therefore, the net intensity of gravitational field should be 0, and that should be equal to gm by x square and minus 16 gm by this is 10a minus x whole square. So cancelling this gm with gm, so this is 10a minus x upon x is equal to 4, and this is 10a by x minus 1 is equal to 4, and 10a by x is equal to 5, and x is equal to 2a. So the distance of this point from the smaller star is 2a. Now we know that in this region, let me show you that in this region the gravitational field of this smaller star will dominate, and therefore the net gravitational field will be towards this star. And in this region, in this complete region, the gravitational field of this bigger star will dominate, and therefore the net gravitational field in this region would be in this direction. So we know that if we need to project this star in such a way such that it just reaches the surface of the smaller star, and we need to give this body a minimum velocity for that. So we know that if we give just sufficient amount of velocity so that it just crosses the neutral point where the net force is 0, then after crossing this point, this star will automatically pull this body towards its surface and it would automatically reach the surface of the star. So we just need to give such amount of velocity to this body so that it just crosses the equilibrium point. Okay, so let us solve this scenario. So we know that in this case we know that initial gravitational potential at the surface of this star is minus 16 gm. This is minus 16 gm by 2a and minus gm by this distance from the center is 8a. Okay, the potential at this point due to this star would be minus gm by the distance of this point from the center, which is 8a. So this is 8a. So the initial potential, you can see, is equal to, this is minus 4 gm by a, in fact minus 8 gm by a, and minus gm by 8a. This is the initial potential at this point. Now we know that the final potential is the potential at the neutral point, and the neutral point is situated at a distance of 2a from the center of the smaller star and at a distance of 8a from the center of the bigger star. So we can say that the final potential will be the potential at neutral point at this point, and it would be minus gm by 2a, and this is minus 16. This is minus 16 gm by 8a. This distance is 8a. So the final potential will be equal to minus gm by 2a minus 2 gm by a. Okay, so it would be equal to, this is minus 5 gm by 2a. Okay, and the initial potential was minus, this is 17, in fact 65, because 8 into 8 is 65 plus 1, 64 plus 1 is 65 divided by 8 gm by a. So the kinetic energy given is half mu square, and that would be equal to the change in work done against the gravity, and work done against the gravity will be m delta v. So cancelling this m with m, u will be equal to under root of 2 delta v, and delta v will be gm by a, and this is 65 by 8 minus 5 by 2. So u would be equal to under root of 2 gm by a, and this is 8, and this would be 65 minus 20, so it would be equal to 45. So this is under root of 45 gm by 4a. This is the velocity with which we need to project this body from the surface of the bigger star so that it reaches the surface of the smaller star. This is the minimum velocity. Okay, now we move on the next question. In this question, you can see that there is an object which is on the surface of Earth, and we need to find out the minimum speed with which we should project this object from the surface of Earth so that it reaches the height which is equal to the radius of Earth. This is r, and this is also r. Okay, so we know that what we need to do is the given kinetic energy half mu minimum square is equal to m delta v. Cancelling this m with m. So u minimum square is equal to 2, and delta v is the change in potential. We know that as we move away from the surface of Earth, the gravitational potential energy increases, and therefore gravitational potential increases. So we should write it down as V final minus V initial. So U minimum square is equal to twice of V final is minus Gm by 2R, and V initial is minus Gm by R. So U minimum square is equal to twice of, this is minus Gm by 2R plus Gm by R. Okay, so U minimum will be equal to Gm by R root. So this is the minimum velocity with which we should project this ball so that it just reaches the height equal to the radius of Earth. Now we move on the next question. In this question, you can see that there is a hollow spherical shell which is compressed to half of its initial radius. So we need to find out the effect of this compression on the gravitational potential at the center of the shell. So we know that at the center of the shell, the gravitational potential is equal to minus of Gm by R, where R is the radius of the shell and m is its mass. This is V. So now what we have done, that we have compressed this shell to half of its radius. So you know that if radius is decreasing, then magnitude of this potential will increase, but obviously it is negative, therefore increasing magnitude means a decreasing potential. So we can say that the potential of this sphere at the center is decreasing. Now we move on the next problem. In this problem, you can see that if the radius of Earth is increased by a factor of 5, and we have to keep the acceleration due to gravity same, so by what factor we should decrease or increase the density? Okay, so first of all, let us see that the formula of gravitational field intensity is Gm by R square. Okay, and this m is mass of the Earth, so we can substitute the value of m as 4 by 3 pi r cube into density. So G is equal to G by R square into 4 by 3 pi r cube into rho, and G is proportional to R into rho, which means that you can see that if radius is increased by a factor of 5, then the density must be decreased by a factor of 5 so that the acceleration due to gravity remains the same. So the correct answer will be B. Now we move on the next problem. In this question, you can see that the mass and the diameter of a planet are twice as that of Earth, and we have to find out the time period of oscillation of a pendulum on this planet if it is a seconds pendulum on Earth. First of all, we know that seconds pendulum has a time period of 2 seconds. Okay, so let's suppose that, and we also know that the time period of SHM of a simple pendulum is t is equal to 2 pi under root L by G. So we can say that T of Earth upon T of that planet is equal to under root of G of that planet upon G of Earth, because this time period is inversely proportional to root G. So this can be the relationship, and time period on Earth is 2 seconds because it is a seconds pendulum on Earth. So this is 2 upon T of planet is equal to under root of G of that planet upon G of Earth. So T of that planet will be equal to 2 under root of G of Earth upon G of planet. So let us substitute the values of G. So we know that G is capital G m by r square, and G would be cancelled out. So this is m of Earth upon r of Earth whole square into m of planet upon r of planet whole square. Now it is given that mass and diameter of that planet are twice to that of Earth. So if the mass of Earth is m, and then the mass of that planet would be equal to 2m, and if the radius of Earth is r, then the radius of that planet would be 2r. So this is 4r square. Okay, so cancelling this r with r, m with m, so you can see that the time period of this pendulum on that planet will be 2, and this would be root 2. So the correct answer will be 2 root 2 seconds. Now we move on the next question. In this question, you can see that there are two identical satellites which are at a height of r and 7r from the Earth's surface. Then which of the following statement is incorrect? So we know that the ratio of total energy, so the total energy is equal to minus gmm by 2r. This is the total energy, where r is the distance of that satellite from the center of Earth. So TE1 upon TE2 will be equal to R2 by R1, and this R2 will be equal to 8R, because the height of the second satellite from the surface is 7R, so its distance from the center of Earth is 8R, divided by this is R, so R plus R is 2R. So this is 4. So TE1 upon TE2 is equal to 4. This is the ratio of total energy of those satellites. So obviously A statement is incorrect. So we have to find out the incorrect statement. Now the ratio of kinetic energy. So you also know that the kinetic energy is equal to minus of total energy, and hence it is gmm by 2r. Therefore the ratio of kinetic energy will also be same as that is of total energy, so it is 4. So this is correct. The ratio of potential energy, and we know that potential is gmm by r, so again the ratio of potential energy will be same, it would be 4. Okay, and the ratio of total energy of both is 4, and the ratio of potential energy, ratio of total energy of both is 4, and ratio of potential energy to the kinetic energy is 2. Ratio of magnitude of potential energy to the kinetic energy is 2. So the incorrect, this is also correct, because magnitude of potential energy and kinetic energy has a ratio of 2. U by k is 2. So this is also correct, but we have to choose the incorrect option. So the incorrect option is A. Now we move on the next question. In this problem, you can see that this is a graph between the energy of a satellite with the distance r from the center of Earth in a circular planetary motion. So we have to find out the correct statement about these three curves A, B and C. So we can first of all write down the formulas. So the potential energy is equal to minus of gmm by r, the kinetic energy is equal to plus gmm by 2r, and the total energy is equal to minus of gmm by 2r. So you can see that kinetic energy would be positive, so A would be kinetic energy graph, and the total energy and potential energy would be negative. Now you can see that for the same value of r, the value of this energy for curve B. The magnitude of curve B for same value of R is greater, and we know that for same value of R, for same R, the magnitude of U is greater than the magnitude of total energy. Okay, you can see that. So there is a 2 in the denominator here. So magnitude of U is greater than the magnitude of total energy. Therefore, B would denote the potential and C would denote the C is total energy and B will be the potential energy because its magnitude is greater for the same value of R. So the correct answer will be option number D, because it says that A is kinetic, B is potential and C is total. Okay, now we move on the next problem. In this problem, you can see that there is a satellite of mass m and it was initially at rest on the surface of Earth. It is launched into a circular orbit at a height that is equal to the radius of Earth. So we need to find out that what minimum energy we should give that satellite so that it gets established into the orbit of radius r, of in fact radius 2r, because its height is r. So we can say that initially the total energy was the potential energy only at the surface of Earth, and it was minus gmm by r. And finally, when it is established in the orbit, then the total energy in the orbit will be equal to minus of gmm by 2r, where r is the radius of orbit, and in this case the radius of orbit is 2r, so this would be 4r. So the energy given is equal to delta E is equal to total energy finally minus the initial energy. So the final energy is minus gmm by 4r and the initial energy is minus gmm by r. So this would be equal to gmm by r 1 minus 1 by 4. So this would be equal to 3 by 4 of gmm by r. This is delta E. Okay, now we move on the next question. In this question, you can see that there is a geostationary satellite in an orbit around the Earth at a distance of r from the center of the Earth, and the angular velocity of the Earth is suddenly doubled. So now we have to find out the new radius of the orbit of geostationary satellite. So we know that the third law of Kepler says that t square is proportional to r cube. So we can say that t is proportional to r to the power 3 by 2. Okay, so this is the relation between t and r, and the omega is equal to 2 pi by t. So we can say that omega 1 by omega 2 is equal to t2 by t1. Okay, so in fact omega 1 by omega 2 is equal to, yes, t2 by t1, because omega is inversely proportional to the time period. Okay, so this is also equal to r2 by r1 to the power 3 by 2, and initially omega was omega and suddenly omega is doubled, so this is 2 omega. So this is r2 upon initially r was r to the power 3 by 2, and squaring this, it will be 1 by 4 is equal to r2 by r cube, and r2 by r will be equal to 1 by 4 to the power 1 by 3, and r2 will be equal to r upon 4 to the power 1 by 3. Okay, so the correct answer will be option number C. Now we move on the next question. In this problem, you can see that the satellite A and B are orbiting around the Earth in orbits of ratio r and 4r. So we have to find out their aerial velocities ratio. So we know that the aerial velocity dA by dt, let us name it as VA, aerial velocity. So this is equal to L by 2n. So VA1 upon VA2 is equal to L by L1 by L2. We are assuming that mass of these satellites is same. So L1 is mvr and L2 is mvr. So cancelling this m and m, and we know that V is equal to under root of gm by r1, orbital velocity, and this is under root of gm by r2. So you can see that this would be under root of r1 by r2, and r1 by r2 is under root of r upon 4r, so it is 1 by 2. So we can say that the ratio of aerial velocities will be 1:2. So the correct answer is A. Now we move on the next question. In this question, you can see that a particle is lifted from the Earth's surface to a height h, and h is very less than r. We have to find out the fractional change in the free fall acceleration of that particle. So we know that if h is very less than r, then g dash is equal to g into 1 minus 2h by r. This formula is valid, and we have to find out the fractional change in the value of acceleration due to gravity. So we know that fractional change would be obviously g dash minus g. So g dash is equal to g into the g minus 2h by r into g, and g dash by g, in fact g dash minus g divided by g is equal to minus 2h by r. So the fractional change will be equal to minus 2h by r. So the correct answer is C. Now we move on the next question. In this question, you can see that if suddenly the gravitational force of attraction between Earth and a satellite revolving around the Earth becomes 0, then the satellite will. So obviously we know that if satellite is already revolving around the Earth, then it's the centripetal force, which is the gravitational pull of Earth, is keeping that satellite into circular motion. So if the gravitational pull of Earth suddenly vanishes, then that satellite would move in the tangential direction like that. So if it is revolving like that, then at this position, if its gravitational field vanishes, then it would move like that. So the correct answer will be it would move tangentially to the original orbit with the same velocity, like that. Okay, now we move on the next question. In this question, you can see that a spaceship has a mass of 1000 kg, and it is to be launched from the Earth's surface out into the free space. The value of G and R is 10 and 6400 kilometers, So the required energy would be, so we know that in free space the final total energy will be 0, and from the earth surface the initial energy of that spaceship will be minus of gmm by r, which is the potential energy. So the energy which is required to be given to this spaceship is gmm by r, and the value of g is this gm is gr square, and m is 1000 kg. So you can see that this gr square, g is 10 and r is 64 into 10 raised to power 5 meters, and this is 1000. So you can see that this is 64 into 10 raised to power 9, and you can see that it is 6.4 into 10 raised to power 10 joules. So the correct answer is A. Now let us move on the next question. In this question, you can see that there are 4 particles which are of same mass m, and they are equidistant from each other like that, and they are moving in a circle due to their mutual gravitational force. So we have to find out the speed of each one of them. So we know that this is a symmetrical case, so speed of each one of them would be same like that, and this radius is r. Now you can see that if the side of the square is a, so we can say that a by root 2 is equal to r, so a is equal to root 2r. Okay, you can easily analyze this situation, that this is a and this is root 2a, and this is half of root 2a, which is a by root 2. So a by root 2 is equal to r. Okay, now we can say that in this case each one of them is applying some gravitational force on the other one. So let us assume that we are talking about this particle. So the gravitational pull on this one due to this one is this F, and the gravitational force due to the mass m is this F, and the gravitational force due to this mass would be F by 2. This is F by 2 due to the fact that this F is gmm by a square, and this F by 2 will be equal to gmm by root 2a square, which is 2a square. So there would be a factor of 2 in the denominator. So this is the net force. So the net force acting on this particle would be like that, F net, and F net would be equal to F by 2 plus 2F cos 45. This angle is 45, this angle is 45. So this is F cos 45, F cos 45. So it is 2F cos 45. And this is being balanced by centrifugal force, which is mv square by r. Okay, and r is the radius. So this is F by 2 plus root 2F, and it is equal to mv square by r. So F is common, and F is gm square by a square. So a is root 2r, so it is 2r square, and here it would be 1 plus 2 root 2 by 2, and this is equal to mv square by r. So cancelling this r with r and m with m, you can see that v will be equal to 1 by 2 under root of gm by r, and this is 1 plus 2 root 2. So the correct answer will be option 2. Now we move on the next question. In this question, you can see that there is a particle which is moving, there is a satellite which is revolving around the earth in a circular orbit of height h from the earth's surface, and h is very very less than r. So we know that in this case, when the orbit is very close to the earth's surface, the orbital velocity is under root gm by r, and the escape velocity is equal to root 2 times of orbital velocity. So the increase in velocity will be equal to root 2 minus 1 into VO. So delta V will be equal to root 2 minus 1 into VO is under root of gm by r, and gm is equal to gr square. So delta V will be equal to root 2 minus 1 into this is under root of gr. So the minimum increase in velocity so that it may escape from the orbit will be under root gr into root 2 minus 1. Option A. Now we move on the next question. In this question, you can see that the variation of acceleration due to gravity g is shown with the distance d from the center of the earth, and it is best represented by. So we know that earth is a solid sphere, and inside a solid sphere the gravitational field intensity is gmr by r cube, and you can see that I is directly proportional to r, and outside it is gm by r square. So it is inversely proportional to r square. So inside the surface of that sphere, the graph would be a straight line, and outside it would be a hyperbola. So the correct answer is second. So these was the problems of level 1 on gravitation and satellite motion especially, and in the next video I would be bringing the level 2 problems which are of Irodov book. You must have heard about the Irodov. So I would be bringing the Irodov problems in the level 2 part in the next video. Thank you.